Okay, so in this video, we're going to use the skills we learned about orbital diagrams to complete the orbital diagrams for these four elements: boron, carbon, nitrogen, and oxygen. But before we do the orbital diagrams, we obviously need to have the electron configuration for each, so we know how many lines or boxes to draw for the orbitals, as well as knowing how many electrons we need to place. So what I have written below each element is the electron configuration for that particular element. So if you need to review how to do electron configurations by using trends of the periodic table, this would be a good time to review that video. It'd also be a good time to have your periodic table in front of you so you can see how we got these particular electron configurations. Okay. So I have the electron configurations written for each element, and below I have written the lines or boxes, if you want to use boxes, and the designation of the orbital for each orbital. So as we talked about in the last video, only each orbital, regardless if it's an S, P, D, or F, each orbital can only have a maximum of 2 electrons. So that means that I can only have a single S orbital, regardless if it's 1s, 2s, or 3s, and I would have 3 p orbitals. And the reason why there's 3 lines here that designate the p orbitals is because when you look at the periodic table, what's the maximum number of electrons that can be placed? Well, there's a possible total of 6 electrons that need to be placed. And if each orbital can only have 2 electrons, then I better have 3 separate p orbitals available to take those if need be. Okay, so there's always going to be a single s orbital, 3 p orbitals, and I know we don't have any d orbitals for these electron configurations, but if we did, we would have to draw a total of 5 lines or 5 boxes to designate those 5 d orbitals, because there's a maximum of 10 electrons that may need to be placed in those orbitals. Okay, so that's why I have 1 box or line for the s orbitals and 3 for the p orbitals. Okay, I need to draw those orbitals regardless if there's going to be electrons placed in them or not. Okay, but let's talk about this first element, boron, and writing the orbital diagram for it. So I have the electron configuration here, and so according to this electron configuration, I need to place 2 electrons in the 1s orbital. And so remember from the Aufbau principle, when we place electrons in orbitals, they go in the lowest energy orbital first. So I'm going to put them in the 1s orbital first before I put any in the 2s orbital. I'm going to have 2 electrons placed in that 1s orbital. And when I place electrons in that orbital, I'm going to use arrows. So I'm going to have my first electron. For my second electron that goes in that 1s orbital, we need to remember that rule that states that electrons that are in the same orbital have opposite spins. That means they point in opposite directions. That's the Pauli exclusion principle. So when I place my second electron in the 1s orbital, I'm going to place it pointing the opposite direction. So I have now placed my 2 electrons in my 1s orbital. Now I'm going to go on to place 2 electrons in my 2s orbital, remembering that the spins must be opposite, so the arrows must be pointing in opposite directions. And now I'm on to my final electron, which is in a 2p orbital. So I'm just going to place 1 electron in 1 2p orbital. So this, minus my chicken scratch down here, this would be the orbital diagram for boron. If we were to do carbon, the only difference between boron and carbon is that second electron in the 2p orbital. We're still going to have 2 electrons of opposite spins in the 1s orbital, 2 electrons of opposite spin in a 2s orbital. And now I have to place a total of 2 electrons in my 2p orbitals. And now here is where the bus seat rule or Hund's rule comes into play. When placing electrons in an orbital that has the same energy, and these 3 2p orbitals have the same amount of energy, we place the electrons in those orbitals singly first, and then and only when we need to double up do we double up. So for my first electron, I place it in 1p orbital. That second electron is not going to be paired because it still has these 2 empty orbitals it can select from. So that second electron goes in a second p orbital. So this would be the electron or the orbital diagram for carbon. Nitrogen, which is again only differs by 1 electron, it's going to be similar to carbon with the 1s and the 2s, but now I have 3 electrons to place for my 2p orbitals. So I have my first electron, my second electron. For my third electron, I still have an empty orbital from the 2p's that I could choose from. So that's where my third electron goes. So there's my electron or my orbital diagram for nitrogen. Then for oxygen. Oxygen has an electron configuration of 1s2, 2s2, 2p4. So I'm going to put my 2 electrons in the 1s orbital, just as I've done previously. Same for the 2s electrons. Now for my 2p's, I have to place 4 electrons in a total of these 3 boxes, in these 3 2p orbitals. So by following Hund's rule, I need to place singly first, and then once I do that, if I need to, then I pair. So I'm going to place my first electron. So when I do that, I now I've placed 1 of my 2p electrons. I have 3 more to place. There's my second 2p electron. There's my third 2p electron. So now I have 1 more 2p electron to place. I don't have any more 2p orbitals to choose from, so I am forced to pair up. So that 4th and final 2p electron will be paired in this orbital, but I need to make sure that that electron has an opposite spin according to the Pauli exclusion principle. Okay. So that would be the orbital diagram for oxygen, using the 3 rules that we talked about previously. Hund's rule, the Aufbau principle, and the Pauli exclusion principle. Now, on the exam, I'm obviously not going to be able to tell you or ask you to draw orbital diagrams, but you should feel comfortable doing orbital diagrams for simple elements like this, and then I can ask you questions about those orbital diagrams. So for example, I could say in oxygen, looking at the orbital diagram for oxygen, what orbitals have unpaired electrons? Well, looking at this, you would see, oh, I have 2p, I have 2 2p orbitals that have unpaired electrons. Another question would be, for nitrogen, how many unpaired electrons does nitrogen have? Well, nitrogen has a total of 3 electrons that are unpaired. So you should be able to do orbital diagrams like this and be able to answer simple questions about electrons in those orbitals.